welcome to the webinar. This is first of an ongoing webinar series we just started with Rafe being the first speaker on special topics in cell isolation. Vitacyte has actually sponsored webinars for human islet isolation since November 2020 with the goal of really having an open discussion forum on topics of interest to the human islet isolation community. I think there's a need just to have, again, discussion is good, sharing of ideas is great, and we are going to initiate and have these seminars quarterly. I really welcome any interest or feedback you have about the quality of the webinars, and also any topics or speakers who you would recommend do a webinar on a topic. We're leaving the whole area of cell isolation open to any cell. The whole goal is to have a forum for discussion. Ground rules are that there's one poll at the beginning of the webinar, 2 polls at the end. Please, if they only take less than 10-15 seconds, fill them out. All the Q&As should be asked through the chat box at the end of Rafe's webinar. We'll go through and have a Q&A session. So without further ado, I will present Rafe. Rafe, I met when he was at Cells Direct, just at the time of Invitrogen. I had been working for quite some time with a year or two earlier with Ed Lecluse to try to see how we could use our enzymes in human or hepatocyte isolation in general. And then Rafe worked, was my primary contact at Cells Direct until he left and went to Ambus, where they also were using our enzymes for the work they did at Ambus. So without further ado, Rafe, welcome, and thank you for doing this webinar.
Okay, very nice. Thank you, Bob, so much. Let me go ahead and share my screen with you all. All right, well, thank you so much for the introduction today, Bob, and it is my pleasure to be here. Also, thank you for having me at this webinar as well, and for the participants, thank you for participating here. So today I'm going to talk about the subject or the area that I've been involved for the last 24 years. It's a very, very exciting area. It's isolation of hepatocytes. And the reason why is it exciting to me, because, you know, when you think about this, you work with human livers. There's essentially gift of life. Somebody has to donate the liver in order for you to isolate the cells from them. And realistically, the best quality livers are used for transplantation. So what you get is something that is not the best. And then being able to generate something out of this at the end, a high quality, high quantity of hepatocytes that people can use for drug discovery, for your research, is really rewarding. So because of this is really exciting. And today, welcome you to my talk about collagenase selection and process optimization for high yield of hepatocyte isolation. So for this talk, I'm gonna chat about 3 different areas here. One is introduction and strategy for choosing collagenase. The second, I will talk briefly about hepatocyte isolation process and how you can optimize it. And then finally, I'll give you some examples and show you what this looks like in the real life. Now, quick spoiler alert, all of this will be about Vitacyte collagenase. Like Bob mentioned, I was introduced to Vitacyte collagenase about 15 years ago. Since then, I really enjoyed working with this team and with this product. It's very consistent, very reproducible, and it does something that many other collagens don't allow you to do, which is optimize the process. And not only that you can optimize the process, but you can customize it to all your isolations, to all your needs, and so on. So on the next few slides, I'll show you how we do that. So first, let me just start some basic information. So as probably many of you know, or maybe not, the collagenase is isolated from Clostridium histolyticum, is essentially anaerobic motile gram-positive bacterium that eats meat. And in order for the meat to be absorbed in the amino acids form, it has to produce enzymes to digest it, and hence it produces collagenase. Now, if you just simply take the supernatant from the culture of this bacterium and you purify it, you end up with the crude collagenase. And this is something that you can potentially see in a Sigma Aldrich catalog or in the lower cost collagenases. Now, they work sometimes quite well, but they're extremely high lot to lot variable. So if you find one lot that works, you may not be able to find another one, or it may take you a long time to really find another lot that will be comparable to your first lot. And the reason for that is when you isolate collagenase, there's not just collagenase in the preparation, there's other stuff. There's other enzymes, there's endotoxin, there's pigment, and all of that interferes with your isolation. Now, on one hand, you do need some protease in your collagenase. So having 100% pure collagenase will not work for hepatocytes, but not being able to control the amount of proteases and what proteases you add is very challenging. So the other option is to get enriched collagenase. This is essentially crude collagenase that have been purified a little more, and then it gives you a little more purity. There's less pigment, there's more activity, and maybe less of this nuisance other proteases. But there's still lot-to-lot variability. As you can imagine, each lot starts differently. At the end of the purification process, you end up with various very variable materials. So it's very inconsistent. Now, how this works in more details, right? So you have two classes of collagenase. You have a class 1 and you have a class 2. And then if you look at HPLC on the left in the chart, you can see those are the first two tall peaks. The first peak is the C2, and then the second one is C1. And then you can see there's this other peak, which is the pigment. And there's all this mass on the bottom. This is all the contaminants that you have in the prep. And this example is actually a really nice example. If you went back and you look at many different crude collagenases, which you actually discover that in some cases you cannot even identify those peaks for collagenase. There's so much other contaminants. So because of that, you have this lot of variability that we're talking about. So on the right, you have a chart where we're looking at the CDA, which is the collagen degradation activity, and you're looking at the black line. It represents the collagenase activity in a specific lot of the collagenase. And the red one indicates the activity of protease. And again, what you see is lot A has a high amount of the collagenase activity, but low amount of the protease. Lot C is low collagenase and low protease. And then lot E is, again, a little bit different. So if you kind of imagine, each lot here is completely different beast. And you have to optimize every single time you switch to that lot, which is crazy. So if you were working for months with one lot and you suddenly switch it, and you have to spend a lot of time, a lot of money, a lot of knowledge to really optimize, this is really challenging. What adds to the damage is that collagenase come in different flavors. So you have a type 1, type 2, type 3, type 4. Just kind of a basic overview of those. The type 1 is just the crude collagenase with original balance of enzymes. Type 2 has higher relative levels of protease activity. Type 3 has the lower level of the secondary proteases. And then finally, the best of all, which is the type 4, which is the collagenase with low tryptic activity. And so what's interesting to know is that when you're working with the non-fibrotic livers, i.e. healthy livers, whether those are mice, rats, or human livers, or any other species, the hepatocytes in those livers are very sensitive to trypsin. So any tryptic activity in your collagenase will destroy them or damage them. So you're not going to be able to cryopreserve them, or you end up with low viability in your preparation. So having collagenase, like type 4 collagenase, that have a low tryptic activity is critical. Now, that said, there are some other instances where you may have a NASH liver or fibrotic stage 4 liver, or liver in a rat after CCL4 after 2 months, which is very fibrotic. In that case, there's so much ECM, there's so much collagen, there's so much other proteins in that liver, then using type 4 may just not work. So you have to think outside the box, and you have to go away from the type 4 and maybe use type 2. In my personal experience, type 2 is very good collagenase for this type of applications. Now, keep in mind, you're not going to get a high yield, you're not going to get a high viability, but you will be able to get decent hepatocytes out of those fibrotic livers. So if you're talking about a high yield, you're talking about high viability, and you want to, to have a very optimized process, you really have to stick with type 4. And that's what we're going to talk for on the next, all the other slides. The collagens that we use is always type 4. So Bob already mentioned, he came to us about 15 years ago, and he brought his collagenase, and he introduced it as it was a very pure collagenase that doesn't need any additional testing. We just simply tested once, and once we're happy with it, the process will always be reproducible. So, we trust but verify. We wanted to make sure that Bob is really telling us true. So we asked him to send us a few lots. I don't remember now exactly how many lots we tested. We did 4 or 5 lots. We did multiple isolations in rats, mice, human tissue. And after a few months, we came back with Bob was right. His collagen is very consistent. It's very reproducible. Even if this different lots, the differences between each lot is so minuscule that you cannot see it at the level of the isolation. Now, it did work differently than what we were used to it. So we had to change entire workflows. We had to develop completely slightly different procedure that would work with his approach. And I'll show you in a second why. But at the end, we're able to really optimize it. And when you see some of the charts that he provided us at the time, his collagenase HPLC, you can see that the peaks for C1 and C2 are clearly defined. There's very tiny peak for pigment, and there's almost no weeds in the bottom, right? There's no contaminants because it's pure collagenase. So that was great. And then on the bottom, you have example of 6 different lots of collagenase, and you can see that the activity of collagenase and the activity of the protease is almost identical from lot to lot. So again, once you optimize the process, you don't have to worry about changing it. You don't have to change the collagenase because each lot that Bob and his company can manufacture is very consistent. So batch to batch, there's no more variability there. The collagenase activity was really strong, and it gave us the power to really make optimization and then set it in stone. So now what I told you about, what is the difference in Bob's collagenase? Well, because he purifies the collagenase to the point where there's nothing else left in there, you have to add protease separately. So that is, on one hand, is more challenging because you may not be used to that. So you have to add it. But on the other hand, it allows you to customize your process for every species and make a best out of each of the approach for each of the species. So here's the secret to the solution. So you have a collagenase MA and protease BP. You simply combine them together using his protocol that he provides you initially. And then from that, you can optimize it further to make it work better. And then you start optimizing it. So you always have to remember that collagenase separates cells from ECM. So your yield will be heavily dependent on amount of collagenase you're using for your preparation. However, your viability and your single cell suspension is heavily influenced by protease and EGTA. So EGTA is the component of the buffer, and I'll talk about this in a second. But basically, those two allow the cells to be separated. And so a good example here is on the bottom, I have a mouse hepatocytes. And well, we didn't really spend that much time optimizing mouse. So we generating some good quality cells, but you can see that some of them are still stuck together. They're clumpy. So that tells me that probably I have to play with the protease, maybe increase protease concentration in my preparation, or maybe I need to increase time that I'm applying my EGTA and the perfusion buffer in the first step of the perfusion to my mouse isolations. But altogether, they work fairly well. So that's what you have to essentially do. You have to adjust your collagenase concentration to maximize your yield. You adjust your protease concentration to get your best viability, and adjust your EGTA timing on your first buffer to get your nice cell separation. And if you do this right, for each species, obviously you have a special, slightly different process. You end up with a really good isolation process. And on the bottom, you have example of mouse, rat, and human. And we also did other species, including pig, and this works for pretty much across, although each species requires its own optimization. And if you have one that works, optimizing to the other one is fairly straightforward, because then you just have to either increase collagenase or increase the protease, and that everything else stays the same. And then you're looking at the yield and the viability in this process. So with that, I show you a little more about how we actually do this optimization. And one thing I wanted to tell you is I like the principle of KS, keep it simple. I like to have everything simple. You don't need to complicate this process. I have never did oxygenation on my solutions. I never use additional buffers. I don't do wash between 1 or 2. I don't do any special formulations. I use simple HBSS buffers with or without calcium. And I just add what I need to add to them to make them work. I don't try to overthink this process. It's a simple process and it works. So how we do it? So on the left in a picture, you can see that we have a buffer one, which is the EGTA buffer. This is calcium free. In most of the cases, the HBSS buffer, and we add to that EGTA. And then again, you can look at on papers out there, or you can just simply look to the information that's provided to you with the collagenase to tell you how much EGTA you have to add. And in the second buffer is just the collagenase. Now here you have to make sure you have a calcium. Calcium is the cofactor for collagenase, and without calcium, you're not going to be able to get this working. So outside of that, you try to maintain the entire process as close as possible to 37 degrees C. Now, so you start with, so once you get the liver ready and you cannulate the liver and you're ready for the perfusion, you start with the step one. Step one is your EGTA buffer, and it has a few reasons why you do that. So number one is it is used to remove your blood from the tissue. So blood is your enemy. If you have an even trace amount of blood, it will inhibit your collagenase, it will inhibit your digestion. So it is critical that you need to make sure that all your livers are perfused efficiently so there's no blood left in there. And how do you do it? Well, you have to inflate the liver. So inflation is, so when you get a resection or you get the liver from the donation, those livers, there's no more pressure from the blood, so they collapse. And when they collapse, all the capillaries essentially close, and then they trap the blood within. And in the rat or mouse, when you're doing in situ perfusion, it's almost the same story. The moment you cannulate and the animal dies, there's no more pressure from the blood, so then the liver starts shrinking. So you need to make sure you inflate the liver to the point where you can open those capillaries. Now, you don't inflate it like a balloon. If you inflate it like a balloon, it will burst and it will destroy the cells inside. So the way to do it, maybe the easiest way to explain it, is when you look at the liver initially before perfusion, you want to inflate it to the point where the liver is about 10 to maybe 15% larger by volume than what you saw before. So you have to use your imagination a little, but you're talking about just inflate just enough so it is larger than when you started originally. And when you press on it, it's still soft but firm at the same time. So this way you know that there is a pressure inside and then you're getting everywhere. And if you do this right, you will see that the liver will quench within about 3 to 4 minutes and all the blood will come out of that. And at that point, you know that your inflation and your blood removal is working. The third reason why you're doing the step one is you want to relax ECAD-adherent junctions and gap junctions between the hepatocytes. And this is done by EGTA, the chelator of calcium that simply is required for those junctions to be established. So once there is no calcium, then those gap junctions relax. And you can typically see that when you start your perfusion process and the liver is already quenched and you look at the liver, it's very uniform in color. It kind of looks like a cappuccino coffee. And then within a few minutes, you start seeing this cobblestone, kind of almost like a hepatic lobule outlined on the liver, like a structure. When you see that, that is exactly telling you that you just got this relaxation and you're getting the separation working. So the process is essentially time dependent. So once you get the blood out, once you do inflation, then you need to ensure that you do this long enough that you separate the cells from each other. So typically for mouse and rat, this will be around 15 minutes. For human liver, it can be anywhere from 20 to 30, maybe even an hour. The rule of thumb is simple. If there is a blood in the liver and you've been doing this for 20 minutes, do it longer because it's a waste of time to perfuse it with collagenase because it will not work. So you need to get the blood out. So whatever methods you can do, including massaging the liver, lightly pressuring it to release the blood, is very critical. So you need to make sure that blood is out and that process is done for a sufficient amount of time. And once you do that, you simply switch to collagenase and start your time. And you start with the VitaCyte recommended enzyme concentration. And then based on the results that you see, then you can optimize it to your process. Now, why I'm telling you that you have to optimize? The reason is that every group is different. And even if you have a friend across the hallway or across the street doing this process, their variables may be completely different than your variables, which means his process or her process may not work in your laboratory. It may give you a good guidance to start it and then get something out of your liver, but then you still have to optimize it for your own process. And we're going to talk about this in a second also, why is that? So then the next is the digestion is the time dependent and the concentration dependent. So if you want a high yield, you need to adjust this concentration of collagenase until you get the maximum number of cells. And in order for that, you need to know how many cells you can get. And that's what we're going to talk in a second about. And then the time is also critical. If you do it too short, that tissue is underdigested, you get a low yield and you get a low viability. If you do it too long, then you end up with overdigestion and all the cells, you're going to end up with humongous yield of cells, but they're all going to be dead or the viability will be very low. So it's, them if you do, them if you don't. You have to be right sweet spot in there. And I tell you in a second where that sweet spot potentially could be. And then you stop the digestion when you see disaggregation on the tissue. Now, because you don't change the enzyme, because if you're using a Vitacyte collagenase, it's always the same enzyme, the same concentration, and the same, the process that you're using. Once you see this disaggregation, you can learn that when that disaggregation happens and at what level it happens, then it's done. Whereas when you're working with different collagenase, like different lots from, like, let's say Sigma, each lot may behave differently, and then you have to relearn the process, when to stop, when it's ready, when it's not ready, and so on. So another advantage, being able to stop this digestion. So let's talk now about what you can expect and what are the numbers that I could potentially get in my isolation. So first, let's talk about the number of hepatocytes, and we start with the human liver, adult. So from my experience, and I typically use this number for my papers and my grant submissions, is somewhere around 100 to 160 billion hepatocytes. Whether it's true or not, I don't know. I heard claims as high as 300 billion. And from my experience, I never see more than 40 to 50 billion hepatocytes that I can isolate per liver. So what is the actual number in the liver? I don't know. But I would say it's a good idea to start with this 100, 160 and expect that you should be able to hit at least 40 to 50% recovery when you do the isolation. For the rat liver, it's very similar. I would expect somewhere around 1.5 to maybe 2 billion hepatocytes, and your recovery should be around 70% of that. And the same thing for mouse. Mouse is about 100 to 150, and another about 70%. And so here are some kind of the initial kind of ideas for how this works. So for human liver, you have to cannulate and you start perfusing. So I typically start with what I call 1/3 flow of the tissue mass. So for example, if your tissue is 100 grams, you'd want it to start with 35 ml of the flow. So this should give you enough inflation, and then you can adjust. If it's underinflated, you increase that speed. If it's overinflated, you decrease that speed. But at least you have this ballpark idea of where to start with. So 1/3 of the liver mass. Second, what I discovered in the past, that the 20 to 25 minutes is the sweet spot for human hepatocyte isolation. And here's the reason why. When it's shorter time, when you're digesting your tissue in 12 minutes, you're blasting it with enzyme. You have zero control of the damage on the cells. And the process is so quick that by the time you react that it's done, you probably overdone it. So at the same time, if you do it for more than 25 minutes, now the cells are they're not exposed to oxygen, they're in hypoxia, and then digestion is maybe not working, not too long. There's some of the cells already being released, and then minutes later you're getting more cells coming. So as you detaching more cells, the cells you already detached are dying. So essentially 25 minutes and more is too long. And you have to figure out how to squeeze yourself into that 20, 25 minutes. And it's a good optimization, because if your process goes more than 25 minutes, after you optimize it, something went wrong. Maybe temperature is off, maybe pump is off, maybe technique is off. Now, if it's slower, then maybe you're overdone on the collagenase, maybe your temperature is too high, maybe your pump is not calibrated and pumping more liquid than you're realizing. But if you get this process, the human liver, adult human liver section, and I typically section the human livers, large human livers. They're just simply too big for me to really work with them, and it's easier for me to work with the resections. Also, my setup is not set up for pumping large volumes, so it's easier for me to do resections. On the pediatric, it might be a different story. I'll talk about this in a second. But if you take adult liver section, on average, in my process, I was able to get somewhere between 20 to 40 million hepatocytes per gram of tissue perfused. And that is with the Vitacyte collagenase. That roughly corresponds to about 20 to 40 billion total hepatocytes, with roughly about 60 to 80% viability. We rarely get viability above 80%, and typically if it's less than 60%, I don't even continue because I don't expect that the cells will clean up to about 90% that I like to have. So usually I discard them at that point. With pediatric liver, it's a slightly different story. Because pediatric livers are smaller, they're easier to work with. They can be sectioned or they can be done as the whole, but they're also easier to get the blood out of them. They're easier to work in general with them. And when you digest them, they digest fully. As a result, you end up with much higher number of hepatocytes than you get typically from adult. On average, I'll generate about 50 to 75 million per gram of tissue, with my best one approaching 110, I believe, million per gram. But those happen rarely. So typically, somewhere between 50 to 75 million is what we would get. And that small tissue typically would yield about 15 to 25 billion total, with initial viability of about 80 to 95% before the cleanup. Now, for the rat isolation, your perfusion flow is typically about 15-20. They're fairly consistent, so you don't have to worry about optimizing it too much. So just make sure that you have the right inflation. And the time, the sweet spot for the perfusion is about 15 to 20 minutes. And on average, we would get somewhere between 0.8 to 1 billion hepatocytes per rat, with about 80 to 90% viability. For mouse, the speed will be about 6 to 10 ml, about 10 to 12 minutes for the perfusion, and you expect to get somewhere between 50 to 100 million hepatocytes with about 80 to 90% viability. Again, it takes time. So the rat isolation and mouse isolation is all about skill. If you're not getting those numbers, you need more practice. Typically with my team in the past, we would process 100, 200 animals just as part of the training before we would able to hit the numbers we're talking to you about. So this is not something you're gonna do it on the first isolation, so you need to practice. But if you do it right, you get a high yields. Now, I'm not gonna spend too much time on this, but the process itself is a little more complex than just collagenase and then the isolation flow speeds and the times. And that's just the first step. You also have a tissue acceptance criteria, donor age, tissue quality, and what the tissue actually looks like. So you need to make sure that your tissue have actually viable hepatocytes in order to generate large quantity viable hepatocytes at the end, right? If your hepatocytes are dead, and then you get them in the tissue and you isolate them, well, I'm sorry. Even if you optimize your process, they're not gonna suddenly come to life. And the same thing for preparation. Whether you do it at 37 or 4 degrees, whether you use Percol or you're using centrifugation, that is also important. How you're gonna generate the cells and what the yield will be and what the impact on the outcomes at the end. And then finally, cryopreservation. Just because you optimize the first 3, if your cryo is not done right, if your cryo is not optimized with the step down process and how you load the cells and how you're putting them in a step down and how you're running them in a step down, then all this effort that you put up front is not gonna work. So you do have to have the cryopreservation optimized as well. But it starts with collagenase. If that collagenase destroys your hepatocytes, it doesn't matter whether you optimize all those other 3 steps. So you have to be critical about which enzyme you choose and how you're gonna optimize your process. So with that, just wanted to mention very quickly that the process is very unique. So you do have to optimize all the steps. It is challenging. If you've never done this before, it will take some time to get this running. If you like me, for me, this is easy. I've been doing this for 24 years. I almost can do every single step in my sleep. So this is very different. But a lot of times when you're working with new researchers in the space, it can be very challenging and daunting of how to set it up. But remember, once you set it up, once it's working, it's very rewarding. You get a lot of good quality hepatocytes. So on the next few slides, I'll show you what this looks like in my past experience. And this is just a very quick kind of overview. So this is an example of one of the livers that we processed a long time ago. It's a pediatric liver. It's very small. You can see my hand and how it fits in essentially between my 2 fingers. That liver is a BMI of 22.3. Tissue weight was 150 grams. And at that specific process, we only used 100 grams of the tissue, so we actually cut it. You can see those dotted red lines that shows you how we cut that liver for the perfusion. The reason why we cut it, we want to have a tissue for formalin fixing. We want to have a tissue for protein, for RNA isolation, and many other other things. So we didn't want to just waste the entire liver for that. We wanted to get cells in that, so that's why it was cut. You can see on the bottom picture what that looked like. You have the 2 of those lobes. They were glued up nicely to make sure that they're almost like a balloon, so we can inflate them. And then you can see inflation on the right. So it is inflated. You can see it's nice and puffed up, and it's bigger than original, but it's not like a crazy inflated with like that's hard as a rock. So that's very critical. So that tissue, the viability of the cell that we isolated at the end of this was post-isolation 85%. The tissue generated 8.9 billion hepatocytes, which roughly represents 89 million per gram of tissue. Once we clean them up with Percol, we end up with 93.2% viability, and we drop the total volume to 7.3 billion hepatocytes. So keep in mind, the cleanup process is the process where you lose the cells, but also remember that if you have a good quality hepatocytes going to the cleanup, you shouldn't be losing good quality heps. You should be only losing the bad ones and the ones that are not viable. Now, this is sometimes very challenging because you can isolate the cells and you test them and you find out that they are 90% viable, or let's say 85% viable, and then you do cleanup and you lose half of them. Well, guess what? They probably were not 90% viable or 85% viable at the start. Either your trypan blue exclusion was off, either the person that counted the cells may need to be retrained, or maybe your trypan blue was not put on the cells for long enough to penetrate the cells and give you the proper result. So check on that, because you shouldn't be losing a lot of cells unless they are fatty. If they are very fatty cells, then obviously that's a different story. You can see that here the BMI is 22. We typically don't take livers that are less than 25 or 26 BMI, purely because the cells will float. But again, if you know that they will float, you can adjust your process and you can make sure you can get at least maximum that you can get out of that. Here's another example. This was a little simpler. We actually did not cut it, so we perfused it whole. It is also pediatric liver, but it's slightly larger. And I told you I do not process the large livers whole. I only process pediatric livers whole. So this one is BMI 21. Tissue weight is roughly 240 grams, and we perfused with 80 ml per minute. Now remember, 1/3 of the volume of the mass. So the mass of the liver. So if the liver was 240, 1/3 of that is 80. Now you can see on the right on the image, I have two arrows pointing to two cannulas. So that's an 80 ml combined, not like 80 plus 80. That 80 plus 80 will swell and destroy your liver. So now whether it's a 40 and 40, that's a different story. It could, because you can see that one cannula is providing solution maybe in a more direction of the right lobe, and the other one is more in the left lobe. It's possible that one was at 50 and the other one was at 30, but at the end they were combined at 80 ml. So what's the end result? End result was actually very, very high viability, despite the fact that when you look at the color of the liver, it looks kind of bloody. But then remember, flushing and removing the blood. Look at the right image. Look how flushed and how clean that liver is. There is no speck of blood inside. Because of that, you know that you're going to get good cells in good yield. So viability was 89%, and we end up with 16.8 billion, which roughly represents 70 million per gram of tissue of cells isolated from that liver. And then after cleanup, the viability increased by about 10%, so to about 96%, and we lost about 5% of the cells, which that's what you would expect here. So it's about 15.2 billion final, with 63 million cells per gram of tissue. Here's another example. This is the large liver, adult liver. So you can see that this particular liver had a BMI of slightly higher. However, this person was actually exercising and eating well. So we assumed that it shouldn't be as fatty as we would think normally, but it was actually at 26. That's not really that fatty. So the liver tissue weight was about 1.5 kilograms, and we cut it. We cut it into two lobes. So one lobe was roughly around 280 grams, and the other one was around 670 grams. Combined weight, the perfused was 950 grams. The first lobe was perfused about 100 ml per minute. The other one was perfused about 140 ml per minute, again, combined flows. And the end result is viability was at 76%. Now, I told you adult livers are slightly different. There are bigger cells. They're easier to damage. Also, the liver is larger, so it's more difficult to hold in your hand. It's more difficult to perfuse. It's more difficult to clean the blood out. So your viabilities will be slightly less. So in this case, 76%, and we end up with 36 billion hepatocytes, which roughly represents about 38 million per gram of tissue, based on the amount of tissue that we perfused. After cleanup, with the viability of the cells increased to 92, with a final yield of 24 billion, roughly giving you about 25 million of cells per gram of tissue. And you have this really cool picture on the right. This is 2-liter bottle with 10 billion hepatocytes. If you ever wanted to see how 10 billion hepatocytes look like, it's a lot of cells. And we had 3 of those bottles. So you can imagine we actually had I believe we had the 2 step downs that were running continuously in 2 cycles to just process all the cells. Now, some little more pointers to that. So on the left, you can see the image of the digestion. And I told you that you have to look for the signs of digestion. So you see that tissue breakage under the capsule. It looks almost like a chunks that's starting separating. from the tissue. And so this is a good sign that your tissue was digested. I don't know the time for the specific tissue, but probably we're somewhere between 20 to 25 minutes, as we always did. And then once you get to that stage, you simply transfer that to the container where you're collecting your cells, and you shake the cells off. Now, when you're shaking them off, here's the thing. It should take you about 3 to 5 minutes to get those cells out. If they fall out like in 10 seconds, you way overdone the liver. That's very digested. Probably the cells are dead. And even if they're not dead, they're not going to survive cryo. They just go too quickly. So that again goes back to what I told you earlier. You do not want to do digestions for 12 minutes for the human liver. You need to go for the 20 minutes or so. Otherwise, you'll be too quick. Now, as long as you do it in 3 to 5 minutes, it should nicely fall out. You shake the liver, and all the cells come out of that. And you should end up with just nothing else but just a little ECM that you can see visible on the third image from the left, and just a small cell stuck around it. Now, so here's the trick. If you ever wanted to work with zone 1 hepatocytes, well, majority of the cells that you get in an early dissociation, those will be usually zone 3 and zone 2. And you have to put a lot of effort to get those zone 1 out because they're stuck very closely to the ECM. So if you want to have like an enriched population of zone 1, all you have to do is just simply take that material that you see here on this picture, transfer it to a new container, and just shake it off there a little more. And then you end up with enriched population of zone 1 hepatocytes, if you're interested with this type of cells for your research. For us, we typically want a mixture of all of them, so we just do all of this in the same container, and at that point, we end up with zone 1, 2, and 3. And typically, zone 1s are easier to get from the pediatric livers, whereas from adult livers, they're much more difficult to get, and you have to have extra digestion potentially to just even release them, just purely because the tissue is so much larger, so it's more difficult to digest uniformly. Now, once you do it, you're gonna be rewarded with this humongous lot of cells. Here's the example of what the 1,200 vials of hepatocytes look like, going to a step down. I just full step down of cells that can be cryopreserved, and down the road can be used by the researchers, by your people, by your team, for the isolation, for the research, for the therapeutic applications or whatnot they want to use them for. Finally, I wanted to show you that this also works in a rat. Like I mentioned earlier, you can get this out in a rat, in a mouse. This is an example of the work that was done as a collaboration with another group in California. And here's an example of the 3 rats. We call them Vitacyte 1, 2, and 3, as you know, they were isolated with Vitacyte. And you can see how clean and how like cappuccino-like those livers looking. So that's how they need to look during the isolation. All the blood has to be removed. Now look at the left lobe, the left liver, the liver 1. It has some red spots, and guess what? When you look at the numbers, it tells you that there was a problem. So overall, when you look at the table below, the yield of total hepatocytes, liver 1 generated about close to 800 million. Second one generated about 1.1 billion. And the last one generated about 8.6 total yield hepatocytes with fairly good viability. However, after Percol, after we cleaned them up, the first liver lost half of the cells. And you can see that the final recovery is roughly maybe 300 million from the original 600. So that tells me that the viability of 81% probably was not 81%. Probably was something worse than that, because we had the process working for the rat 2 and 3, which means the process was fine. So most likely something happened in the counting. So again, blood in the tissue is a bad news. You don't want that. But in the 2 other examples, you can see that we went from 1 billion to about 900, and from about 800 to about 600, with a 93 and 95% viable hepatocytes that went to cryo, that recovered perfectly and could be used down in other experiments. So it can work really nicely in this process as well. So with that, I just wanted to quickly conclude. So hepatocyte isolation is a very highly variable process. You need to understand it from the start. And the key to success and to get a high yield isolation is to control all your variables: tissue, buffers, process, handling, and collagenase. And collagenase is one of the variables that can be controlled by simply using a Vitacyte collagenase, which is consistent, which is customizable, and you can optimize it really well to get a really good results with the high yield and high viability and for your isolation. And the last thing that I just wanted to quickly mention, most of the work that I do is not used fresh. Most of the work that I do with the hepatocyte isolation goes to cryopreservation. So all the stuff that I showed you It applies to the cryopreserved of hepatocytes at the end. Everything is done to ensure that once you create the bank of cells, they can be used for years after that, and they can have a good quality, good functionality. And again, that enzyme is actually working really well for this approach, and I highly recommend it. So with that, just a quick acknowledgement to the people where this came from, and I learned all the process. Thermo Fisher and Life Technologies, this is where Bob mentioned meeting with Ed Lacluse and learning about the process from him and his team, and then the rest of the Thermo Fisher and Life over the next 10 years. This is create the foundation for the work that I showed you today. And then colleagues from Ambis, Aspect, and Abios, where I was able to apply the knowledge and help generate cells, and see that we could generate those high quality, high quantity isolations. And finally, Dimension Inc. This is my current company for letting me to do this webinar today and supporting me in this effort. So with that, thank you, and I'm open to questions.
Okay, great. Thank you very much, Rafe. This was superb. I mean, really superb, because we used, getting into that level of detail is excellent for a user. And I think that what you said about it's a whole system you have to control, not just the enzyme. The enzyme's a critical part. And what we try to say, and the same thing applies to us supporting human islet isolation, the tacit knowledge, the differences between somebody who gets great yields versus somebody who gets bad yields or average yields is just, how do I say, there are adjustments made on the fly, so to speak. And I was really good to talk to that.
Yes, so this is actually very critical, because each liver that you get is different, especially when it comes to human liver. It could be more bloody, less bloody. It could be larger, smaller. It could be more fibrotic, less fibrotic. So you have to know in and outs of the process in order to make those changes on the fly. Now, that said, the process is fairly consistent. So if you're able to build that process with that consistency, where you have the enzyme consistency, buffer consistency, timing consistency, there's just small tweaks to just adjust to the raw material you get and you're working with.
Yeah. No, again, everyone comes to us and says, well, the enzyme didn't work. And we look at our biochemical data and say, no, it works. The other thing I wanted to ask you is, because as you know, we did the initial work with Steve Strom and Roberto Gravagnoli. And the interesting thing about their system was they used a closed system, actually very similar to islets. And you're using a perfusion system. So the question I have for you is, have you ever done, do you know that my own opinion is perfusion systems for some reason means you use, recycling systems for some reason means you're going to use a hell of a lot more enzyme. And I've always thought that, in fact, what was happening is you could be inhibiting some of the collagenase, which is why, they're using 3 times the amount of collagenase to do human islet isolation versus you. And I was wondering, did you have any knowledge of comparing just the recirculating versus the open systems, perfusion systems? Have you ever seen anyone do that? Does this, what I just said, make sense?
So typically, from my experience, people would want to use recirculating systems so they can save on collagenase, because they'll simply take the collagenase that goes through the system and then recirculate it again. From my experience, I don't like this method, because as we're talking about optimizing the process, I need to be in control of knowing how much I load into the liver and how much is being perfused throughout the process. So if I recirculate the enzyme, What if in one case I get the enzyme that degrades or digests and becomes less active over time?
Yes.
How can I control that? I cannot control that. So then
Yes.
that becomes a variable. So I told you I want to control the variables. So I try to minimize anything that can potentially add this variability. So having this process where all the time I'm delivering controlled amount of collagenase, where I can control the process is I can slow down the flow or increase the flow, or I can give more time to the flow, but everything else stays constant. Now, in my experience, that works. And that is the reason why I'm using it. Now, the groups that may be using more collagenase, I think a lot of times what I discovered is they simply wanted digestion to happen faster, like 10 minutes. I don't understand the reasoning behind it because I told you earlier, you're essentially blasting your liver with the enzyme, and the cryopreservation at the end may just not work well when you finish with the process. Right. So, but then take it again from a different angle. Maybe they have fibrotic livers. Maybe those livers are more difficult to isolate the cells because the BMI is 30 plus and they're coming from adults with fibrosis, in which case you may want to use higher concentration to get those cells out.
Right. Justin Manuel asked a question, will the concentration of calcium affect the digestion?
Yes, yes. So the trick with calcium is to simply saturate your buffer. So if you put more, it will just precipitate. So again, another variable you can control. Once you put saturated calcium in your buffer, you just play with your concentration of enzyme at that point.
Yeah, we get this question a lot, and there's a lot of debate in islet isolation whether you should add more calcium, but Hanks has 1 millimolar calcium, which should be sufficient.
Yeah.
So Ryan Schultz asked, excellent and informative. Can you comment on the inactivation of the collagenase protease following digestion? Is there any benefit to allowing the digestion to continue following capsule disruption? Or is the recommendation to immediately chill the cells once removed from the organ?
So first, very good question, Ryan. Very nice to see you here at the webinar, and I'm glad that you were able to attend. So the first question is, yes, we did try. So you would call it 3-step. So sometimes you introduce the third buffer that contains either high concentration of BSA or high concentration of for example, FBS, and you can simply use it to inactivate collagenase in the liver before you transfer liver outside. Personally, I found this is outside of my KISS. It's too complex. Another buffer, another step to worry about, and at least from the kind of a procedure that I showed you as the description, to maintain the 20 minutes to digestion and then stop when you have the signs and you transfer to the bath where you shake the cells off. We did not need to stop that collagenase. So that's from my perspective. Now, keep in mind that your inactivation, in my opinion, and I might be wrong because I'm not an enzymologist, but it should not apply to collagenase. It only applies to your proteases. And since those proteases have a very low tryptic activity, essentially trypsin, there's not much to inactivate, right? So I think if you're using sigma collagenase, you may have to inactivate. But if you're using Hepatocyte collagenase, there's really truly not much to inactivate, in my opinion. I think the last question was what do you do with chilling versus not chilling. So so when I went in my academic years for 10 years, all my isolations were done where once the cells were separated, they would go on ice, and then the entire process was done on ice. So first thing first, Percol doesn't work in a cold solution. Percol requires 37 buffers, which means if you do Percol, you cannot do cold, and if you do cold, your Percol is not working, and you may not know that. So you may have to come up with different ways of purifying the cells, like centrifugation or elutriation or some other methods. The other reason I don't like to do it, and I don't know how to explain it in a good way, but think about a patient that will die in 2 minutes. Is this patient alive or is this patient dead? So if you isolate hepatocytes that are under damage and you chill them, you essentially put them in this kind of a suspension state where if they're supposed to die in 5 minutes or 2 minutes, they're not gonna die. So you're gonna carry them over all the way to the end of the process to cryo. And then when you recover them from cryo, suddenly half of your cells died off. So I believe, and from my experience, I've seen this in my past, where if you do this at 37, all those strugglers that are dying, they will die off in your process. And then you're transferring only the cells that are robust and can survive cryo. So typically at cryo, my rule of thumb is once they go to cryo and they emerge from cryo, they should not drop in viability more than 10%. And 10%, to me, that's already high. So you should be somewhere around 5 to 6% in drop. If you see more than that, that means your process was somehow masking all those cells that were dying, and then you end up with more cells being dead in there. Now, again, it's up to you how you want to do it at the end. Personally, like I said, I switched to 37. I live by 37, and I live by simplicity. So I don't introduce any additional methods or anything else. Now that said, cold has advantages. So depending how you look at this, there are ways that you can incorporate cold process as well.
Okay. Wadad Waga asks, thank you, Ray, for your presentation. I have a question. Which enzymes contribute to low viability collagenase or protease?
Protease.
Yeah.
Protease. But it's also you're technical, right? So if you squeezing the tissue too much, if you pipetting them too much, if you increasing pressure in the liver, that will all damage those cells. Remember, the easiest example that how I was told in the past, hepatocytes like balloons, and your hands are like razor blades. If you touch them incorrectly, they're gonna. So viability is not just the protease, but it's also your method itself and your handling.
Okay, Julian, almost. Can you get high viability from advanced MASLD tissue? I don't know what that means.
That's a MASH. Oh,
the NASH thing. And how can you quantitate the amount of fibrosis?
Well, so quantitation of fibrosis is outside of the scope for this webinar. But if you wanted to quantitate, I mean, there are different assays and stains you can use it. I forgot what's the other way to do it. Yeah, if I remember, I tell you. But if I don't, you can find me on LinkedIn. Ping me on LinkedIn. I can tell you more about this and how to do this kind of a quantitation. Oh,
it's serious
hydroxyproline. There you go, hydroxyproline. You can do hydroxyproline assay, and that assay is as the quantitative measurement of the collagen in your tissue. Now, in respect to whether you can get a good quality hepatocytes, so the challenge is if you have nodules and those nodules are surrounded by ECM, your perfusion, you have to get to those nodules. You have to get to the inside. And unfortunately, there's no easy way to do it. So the end result is that you can end up with decent quality. I wouldn't say that there will be high quality. You can end up with decent quality of cells, but also your yields may be fairly low. If you're talking about the tissue that's maybe stage 2 or 3 fibrosis, before you get bridging and before you develop those nodules, it's just more fibrosis. So you still should be able to perfuse it fine with the collagenase type 4 or Witek collagenase and get a good quality hepatocytes. Just that kind of the final stage, the cirrhotic tissues and late fibrosis, those are very challenging.
Just to let you know, I mean, this is a real issue in the islet world because, in essence, in the United States, the most common clinical aspect of islets is this total pancreatectomy auto islet transplant. So these organs, literally bricks.
Yep.
I mean, they are bricks. Now, the interesting thing is that the acinar tissue is just depleted. So you don't have a lot of acinar cells anymore, but you have a lot of fibrosis. And what's the sense, believe it or not, in that they're getting recently a couple of centers, it's actually the collagenase that's very important, not the protease. You can drop the protease, which surprised us. So, because I always thought that the collagenase accelerated the protease accelerated the digestion of the collagenase, but the collagenase does well by itself.
Yeah, it could be highly possible that you have so much of the collagen. So essentially, collagen in a fibrotic tissue is not just the collagen type 1, type 4, but you're also going to end up with type 3, type 10, and there's so much more of that, right? So maybe you just need so much collagenase to shoot all of this out.
Yeah.
Now, when you think about liver is a little more complex. Well, maybe, okay, because I don't know enough about the pancreas and the fibrosis there. To really claim, 100% that I'm right on this. But in the liver, you have fibronectin, you have laminin, you have all their ECMs as well. So it's not just the collagen, even in a fibrotic tissue. So because of that, it's still challenging. Even if you just increase the heavily concentration of collagenase, you may not be able to get those cells. In my past, I think I mentioned at the beginning, when we did the mouse model of I think it's called DDC or something like that. When you put them on the chow, DDC chow, and then it leads to the liver stem cell activation, those liver become extremely fibrotic. I think at that time, the only collagenase that worked was type 2.
Oh, really?
And it was like it was like almost like looking for the crude collagenase type 2 that would work in that system. But once you found it, it would work. But again, the yields were not really high. And the viabilities were also on academic level. So like 65, 70%, we were happy we were getting cells at that time.
So I'm going to just end up with this, because I think we don't have any other questions, end up with this comment. We worked with Roberto Gramagnoli and Steve on developing, at least getting a mixture that people would start to use. The interesting thing is what you said is exactly what he said, the recirculating system. You want it around 24 minutes, right? Yeah. And we adjusted. We started using thermolysin. And the problem with thermolysin was that is a bad enzyme for hepatocytes. It was actually significantly lower viability. It's not by a lot, but it was a significant difference. So what we ended up doing, we matched the same activity with the BP protease or dispase. That was too hot. So we cut it in half. That was too cold. And we went in the middle, and sure enough, and that's the 1.1 million units per liter with the first recommended. That was just right. It was 24, 25 minutes that they wanted. So, anyway, and the other thing, just to clarify one thing, all the types you're referring to is the Worthington collagenase, which Worthington makes a very interesting product because the collagenases for 1 through 4 actually, believe it or not, are the same.
Oh, interesting.
I didn't know if you knew that. They're all the same. They bottle based on collagenases. The other things, it's either this is like what Charlie Worthington did. This guy, Charlie Worthington, started the company. He was a tech for Kunitz, believe it or not. He started in 1947. He was a tech for Kunitz, and he would get all this enzyme work that was at the universities and set up a garage biotech shop. Mm-hmm. And type 1 was just the standard stuff they got. Then they found out that people wanted variations. So that's where you got the high protease, the low protease, or the regular protease and trypsin. And so just FYR, we used to have a DE product line. We've simplified it and called it PD now, PD collagenase 100. That's identical to Worthington type 1, but it doesn't have clostropane.
Oh, I see.
Yeah, so.
Interesting. Well, good to know. I think there's something new that I can always learn. So like I said, I'm not the enzymologist. I know what I know. So I'm really glad you actually clarified that and let me know.
Yeah, no. And the other thing, just to let people know, Sigma's system is completely different. Their type 1 is because the way Sigma works is they used to bring in product. So the type 1 you still see in the Sigma catalog is probably the Worthington Sigma. The type 1A is probably the one that they made. But when they did all their different types, they based their activities I mean, they base their release on actually isolating the cells. So that's why you can make hide or hair of the biochemistry that you showed. Anyways, so that's my comment for the history of collagenase, I guess. So again, I think we're going to sign off. I don't see any other questions. I hope you enjoyed the webinar, and please fill out the polls, and don't hesitate to contact me for any further topics or speakers of interest. The goal is to hold these once a quarter. Again, thank you very much.
Thank you, Bob. And thank you the same for everyone as well for attending. And again, like I mentioned, I'm on the LinkedIn. If you have any questions, you can find me there, and I'll be happy to answer them. Thank you again for having me here.
Thank you. Bye.